Chapter 12, we're going to talk about square matrices. So basically what we're going to do in this chapter, we're going to look at the less set of operations that we can do, but only for square matrices. So we can add, subtract, multiply, scalar multiply matrices of any size, but the computation of a determinant or the inverse is something specific for square matrices. So first definition, what's the determinant of a y by 1? So I'm really just introducing this definition for the sake of completeness, but we're not going to be spending too much time. So if you have a 1 by 1 matrix where the entry is A, then the determinant is just the entry itself. So not super interesting, so kind of pointless even. So the real first definition will be what happens if we want to compute the determinant of a matrix that is 2 by 2. So real good first definition. So what's the determinant of a 2 by 2? So if we have a 2 by 2 matrix, the determinant is given by the following formula. So the determinant of A is AD minus BC. So how do you remember this formula? I think the best way to do it is to think about it like Guy Beaulieu. So when he says that he sees a fish, so it's very similar to what we did when we were doing cross product computation. So if you draw a fish in there, you can go AD minus BC, and the mouth is basically the minus symbol here. So when you're following the tail of the fish starting at the top left corner, so you're going A times D minus through the mouth B times C, and that's your formula. So let's just do some examples right away. So here we go, a bunch of examples. Let's compute some determinants. So if you compute the determinant of the 1 by 1 matrix minus 2, you're just getting the number out. So this is my only example that I do a 1 by 1. I will not ever do a 1 by 1 example again. So let's compute the determinant of 3, 7 minus 2, 5. So if I use the fish idea here, here we green. So you're going to get 3 times 5 minus 7 minus 2, so you're going to get 29. And then next example, what's the determinant of the identity matrix I2? Again, if I use my fish here, okay, so you're going to get 1 times 1 minus 0 times 0, you're just getting a 1. And last example, let's compute the determinant of 2 minus 6 minus 10 and 30. So if I use the fish to compute stuff, so you're going to get 2 times 30 minus 6 times minus 10, and you're getting a nice 0. And that's it for 2 by 2 matrices. Next up is the notion of the inverse of a matrix. So the inverse of a square matrix. So definition, the inverse of an n by n matrix, A, is a new n by n square matrix that we denote a to the power minus 1, such that if you multiply A by A inverse, you get the identity. Or if you multiply A inverse by A, you get the identity, where I, again, is the identity matrix. This definition is very similar to how you would define the inverse of a number. So, for example, what's the inverse of 5? Well, it's 1/5, because if you multiply 5 by 1/5, you're going to get 1. Of course, if you go 1/5 times 5, you get 1 also, because product is commutative in with real numbers, but for matrices, we don't have commutativity, so we have to check both directions. So first example, find the inverse of the matrix A between the following two. So when we have candidates for inverses, the only thing we have to do is multiply. So if we try with the first one, so if we have 3, 1, so we want to check if the first one is the inverse. Of course, you can kind of foresee that this is kind of a trap. The only thing I did with this first example matrix is I flipped all the numbers, and this is really just to make you realize that when you're computing the inverse of a matrix, you're not just going to flip all the numbers inside. So if you're multiplying these as matrices, so again, you're using the column falling down on rows, so you're going to get 1 plus 1/5, 5 over 3 plus 2 over 5, and then you're going to get 3 plus 1/2, and then finally 5 plus 1, and clearly this is not the identity matrix, so this is not the inverse. So sadly for that matrix, it's not going to be the inverse. If we try the other one, that's for the first one. So if we try for the other one, so if we have 3, 1, 5, 2, and we multiply it by 2, minus 5, minus 1, 3. So if you do your multiplication, so here again, rows versus columns, and then when you multiply, you get 6 minus 5, you get a 1, and then for the second row, you get 10 minus 10, which is 0. For the second row falling down, second column falling down on the first row, you get minus 1 plus 3, which is 0, and then minus 5 plus 6, which is 1. So that's the identity matrix, which check. So if we flip the roll here, just to be sure, so 2 minus 1, minus 5 and 3, multiplying 3, 1, 5, 2. So it's good review of matrix multiplication at the same time. So my rows for the right matrix and my columns, my columns for the right matrix and my rows for the left matrix. So you're going to get 6 minus 5, which is 1, minus 15 plus 15, which is 0, and then second column, 1, 2 falling down, so you get 2 minus 2, which is 0, and minus 5 plus 6, which is 1. So we get the identity matrix. So that matrix here is indeed the inverse that we were looking for. But of course now the goal is how do we compute that inverse? So the philosophy of this chapter is we're dealing with the 2 by 2 case right away for determinants and inverses. So we have a formula that computes the determinant of a 2 by 2 right away, and now I'm going to give you a formula that computes the inverse of a 2 by 2, and then we'll move up to higher dimensions. So here's the inverse of a 2 by 2. So if you start with a matrix A, given by A, B, C, D, and you want to compute the inverse, so the inverse only exists if the determinant is not 0. So every time you want to compute determinant, and this is true in general, you have to check if the determinant is not 0. And then if it's not 0, the formula is, well, you go 1 over the determinant. So it's important that it's not 0. If not, you're going to get a fraction or a coefficient where the fraction in front of it is 0. And then what you do is you swap the position of A and D, and you change the sign in front of B and C. And this is how you construct the inverse of a 2 by 2 matrix. But again here, very important remark, this is only for 2 by 2. We will find a way to compute the inverse for n by n, and I'm expecting you to be able to do that on a test. So let's do some examples. Okay, so find inverses if possible. So the first thing you always do is you compute the determinant. So if you compute the determinant of 3, 1, 6, 2, you're going to get 6 minus 0, minus 6, sorry, which is 0, so no inverse. Next example, so what's the determinant of the identity matrix? We've done this one earlier, so it's simply 1, so there is an inverse. So let's compute B inverse. So B inverse is 1 over the determinant, which is 1, And now what we're doing is, so let's just make some distinction here. So let's just put a little mustache to this guy here. So we're going to swap the ones. So one will come here, up here with the mustache, and you're going to get -0, -0, and the other one goes in that corner. And of course, what you're going to get the identity matrix. So this is not a surprise. The inverse of 1 is 1, so the inverse of the identity is the identity again. Now for the last example, if you compute the determinant of C, so 2 minus 1 minus 5, 3, you're going to get 2 times 3 minus 1 times -5, which is simply 1. So if you're computing C inverse, you're getting 1 over the determinant, which is 1 here. Maybe I'll use color just to make it clear. So the 1 here, I'll put it in green so that you see where it comes from. Equal to 1, so it's 1 over 1. And then for the rest, so the way it works is you're going to swap the 2 and the 3, so the 3 goes up and the 2 goes down, and you're changing the sign of the other one, so you're going to get minus -1 and minus -5, and then you're going to get 1 over 1 is just 1, then just don't need to write it down, so you just get a 1, so 3, 1, 5, and 2, and that's the inverse. So of course, this matrix here, you might remember it from example 12.2.2. So just a small remark here. So now we know how to compute the determinant of a 2x2 and the inverse of a 2x2. Now the goal is to do the exact same thing, but for matrices of different size. So the goal is to go and compute determinants for matrices and inverses of matrices, not just for 2x2, but for n by n in general. And what we need in order to get there is some little preliminaries, the notion of minors and cofactors. So it's a very purely algebraic definition, but it's the key in order to be able to compute determinants for matrices bigger than 2x2. So first definition, what's a minor? So the minor at the entry Aij, so on the ith row jth column that we're going to denote by big Mij, is the determinant of the submatrix n minus 1 by n minus 1 that you get from A by removing the ith row in the jth column. So you create the submatrix and then you compute the determinant, and that's the minor. And then the cofactor at the entry Aij, which we denote by big Cij, is simply the minor but multiplied by plus or minus 1, depending on if minus 1 to the power A plus j is 1 or minus 1. So let's do some examples. So example, so we have this matrix A, and we want to compute A, the minor M11, the minor M23, and the minor M31, and their corresponding cofactor. So let's do them in pairs. So if you are computing M11, so what you have to do here at M11, so you are creating this determinant of the submatrix. So here I'm going to write it the long way so that you can see it. So the submatrix, so you're at 1, 1. So if I write the full matrix first, you don't have to write the full matrix, but just to show where it comes from. So since we're doing M11, you are at the entry 1, 1, and what you do is you remove, and I'm going to use a marker in red here, you remove the first row and the first column. This is where 1, 1 is, and this gives you this sub 2x2 matrix. Which is simply -3, -1, 0, 3. And if you use the fish, you get minus 9. You get minus 9 minus 0. So you're just getting minus 9. So minus 9. And then the corresponding cofactor. So the corresponding cofactor, C11, will be minus 1 to the power 1 plus 1 times minus 9. So in this case, it's just 1 times minus 9, and you just get minus 9 again. So next one is the cofactor, the minor at 2, 3. So we need to create a submatrix. So either you do it directly, or here I just want to show you where it comes from. So I have 1 minus 5, 4, 2, minus 3, minus 1, minus 7, 0, plus 3. So first let's find the entry that we want. So 2, 3, so second row, third column. So we're talking about minus 1 here. So I'm going to remove the row where minus 1 is and remove the column where minus 1 is. So this will leave behind this submatrix 2 by 2 submatrix 1 minus 5 minus 7 and 0. And then if you use your fishy product, you're going to get 0 minus 35. So you get minus 35. And now for the cofactor 2, 3, it's just minus 1 to the power 2 plus 3, which is 5. Minus 1 to the power 5 is minus 1 times minus 35. You're going to get 35. And we just add up the fish here so that you see them. My fish. Fish. And last example, M31. So we're going to compute the determinant at, so again, let's rewrite the matrix. So now we're at 3, 1. So first you find where 3, 1 is. So that's minus 7. And then you remove the row where minus 7 is and the column where minus 7 is. This leaves behind this submatrix 2 by 2. So you get determinant of minus 5, 4, minus 3, and minus 1. So if you do your fishy, you do your fish, hello. So if you use your fish, you're going to get plus 5, plus 12. You're going to get 17. And then if you're computing the cofactor at 3, 1, you have minus 1 to the power 3 plus 1, which is 4 times 17. So you're going to get 17 again. So remark here, if you want to see the link between the cofactor and the minor, the cofactor is always plus or minus the minor. And actually, it depends on, you can use this little checkboard trick that on the top left corner, it's always going to be a plus. And because when you're moving, let's say sideways or down, you're going to go from even or odd. So 1 plus 1 is even, so you're getting your positive entry, but then 1 plus 2 is odd, 1 plus 3 is even, 1 plus 4 is odd, 2 plus 1 is odd, 3 plus 1 is even, and etc. So you're always going to alternate between plus or minus. So if we go back to our previous example, normally the first thing I like to do when you have to compute minors and cofactors is to draw that checkboard pattern. So this is a plus position, minus, plus, minus, plus, minus, plus, minus, plus. So when you're computing cofactors, like we did, for example, the one at 1, 1, we saw that minus 9 did not change sign because you're at a plus position. The one that we did at 2, 3, the minus 1, it did change sign because I'm at a minus position. And the last one, the 3, 1, that position minus the minus 7 here is at a plus position, and you can see that the minor and the cofactor did not change signs. So you can just use this checkboard pattern to get the cofactor quickly without computing this annoying -1 to the sum power. This is kind of a redundant computation. You just change the sign if you're at a minus position, or you do nothing if you're at a plus position. And this trick is very, very useful. And of course, right now you might have the feeling, well, okay, this works for 3 by 3 because minors are 2 by 2. But what will happen when you have to compute minors or cofactors of matrices bigger than 3 by 3? And actually here, and we'll see this in the next section, that the actual definition can be reused over and over again, so that as long as you know how to compute determinants of 2 by 2s, you're good to go for bigger dimension. I'll just show you how to break bigger matrices into pieces. And this is what we'll do.